have Rosemary Carroll. She goes by Ro, Dr. Ro, joining us from Crested Butte, Colorado at high elevation. I've known Ro, I think, for about 15 years. I was trying to think how far back we go. Ro did her undergrad back in Maine, but then moved out west and settled in Reno for a long time. And we overlapped and worked together while we were both at the Desert Research Institute before I came to UNM. But she's continued on in that role with the Division of Hydrologic Sciences there. And a while ago moved up to Crested Butte, where naturally she has really started to work on headwater related, snowpack related type issues, which I know a lot of people who are on the call today also have a strong interest in. So with that, I'm happy to turn the screen over to Dr. Carroll.
Yeah, well, while I work on sharing my screen, I just wanted to highlight that Mark actually served on my dissertation committee, which was on mercury transport and bioaccumulation. So very different than what I'm talking about today. And to just highlight that there's a versatility in research. You can sort of move around in the hydrologic sciences, which I am a hydrologist, and move around as interest and opportunity dictate. There's just a ton to do out there. And my love of the outdoors is naturally embedded within sort of these headwater systems and really focusing on snowmelt to streamflow. The paper's major, this talk's major through line is going to be 3 papers that we put out that are really looking at stream water source. And I'm going to say with emphasis on groundwater to streamflow. We're going to look at how we can look at the importance of groundwater in these mountain streams, but through a variety of different approaches to try to converge on a common conceptual model. So I would be completely remiss if I pretended that all this work was just me. It really takes a village, and I'm going to add a funded village. I rely on a ton of people that help me better understand watershed sciences. It's very complicated. There are a lot of different processes involved. And so I rely on individuals for their, not only their expertise, but also their generosity in the field and generosity in the lab. And so this is just sort of a short list of those that are immediately on the papers I'm talking about, but this list is actually much longer than this. So I know I'm probably preaching to the choir here. Most of us on this call are likely familiar with the Colorado River and how important it is. It is important environmentally, it's important economically. So just to give a sense of it, the Colorado River in the southwestern United States, it is supporting probably about 40 million people and $1 trillion annually in economic activities. It's incredibly important regionally. It receives about 90% of its water from the snow-dominated headwater systems in Colorado, Wyoming, and Utah. And the East River, where I'm going to be talking about, is very emblematic of these headwater systems. And you can look through the literature. There's a lot of wonderful research out there, all pointing to the idea that these southwestern systems, and the Colorado is somewhat emblematic of them all, as a system that is under a lot of stress. It is seeing over the last 40 or so years declines in peak snow water equivalent or accumulation. It's seeing increases in the duration and the frequency of snow drought. And in this recent paper it came out in Science with Milley and Dunn, showing that increased temperatures drive changes in albedo, increases in evapotranspiration, and fairly significant declines in stream flow. So the East River, as I just mentioned, is emblematic of these sort of cascading effects, and it's located near my home in Crested Butte, Colorado. It is also home of the Department of Energy's funded Watershed Function Science Focus Area, or SFA. This is money that goes through the Lawrence Berkeley National Laboratory, and LBNL's key grand challenge question that they've posed is, how do these mountainous systems, how do they store and retain, or how do they retain and release water, nutrients, carbon, metals, from very short, say, seasonal episodic timescales all the way to sort of decadal, even multi-decadal timeframes. So the work I'm going to talk about here really fits into the grand sort of context of LBL's work on watershed sciences and mountain systems. So I'm asking 3 questions. I'm going to try to answer these questions today. The first question is, how important is groundwater to stream flow in these mountain systems or within a mountain system? What are some of the first order controls on groundwater recharge? And how bold is base flow. And I'm standing on the side of a mountain within the East River Basin called Snodgrass. And I'm looking across this image here, this photo, I'm looking across the East River main stem over to Copper Creek. So Copper Creek is eventually going to be our primary research site. So I just wanted to give you some context of scale and topographic complexity. Now, in these topographically complex systems, we have several challenges in answering these questions. The first real challenge is that we need to be able to try to quantify in both space and time the codependent relationships between climate, topography, vegetation type, and structure. And if we're going to talk about groundwater, we also need to link in geology. So all of these work together in some shape or form in space and time and at relatively small spatial scales to drive stream water source. The other challenge we have is that these systems tend to lack data. There's a lack of data due to access issues, but also, again, getting at the important scales, driving hydrologic processes with emphasis on, say, ET or evapotranspiration, snow dynamics. And in this talk, I'm going to actually focus on the difficulty in trying to parameterize the subsurface, where we just don't have a well field, right, drilled into these 14,000-foot peaks. So because by my estimates, the East River gets about 80% of its water inputs is from snow, we're going to start off by talking about snow observations. We're going to look at this first in terms of temporal variability. And I show this through a snow telemetry or SNOTEL site. I'm showing SWE traces, and SWE stands for snow water equivalent, over a multi-year period. So from 1987 through 2018. And what you can see here in these SWE traces, it's at the interannual variability on peak snow water equivalent, as well as when the snowpack melts out, is highly variable within the historic period. So for this time period, 1995 represents a very, very wet year, high snowpack, late meltout date, while 2012 represents the other end member being very low snowpack and very early meltout date. Now this yellow line here represents 1998. This is the median condition, and I'll kind of keep coming back to this condition as we move toward modeling. In terms of spatial variability, I'm going to rely on the Airborne Snow Observatory, or ASO. This is a LiDAR-derived product in which they fly a fixed-wing aircraft over your watershed when there's no snow, and then they fly again when there is snow, and then they take a difference. And the resolution and snow depth is very, very fine. It's at 3-meter resolution across your watershed. There is an upscaling to get to snow water equivalent, and they do this through snow density modeling, and then we use on-the-ground snow pit validation for that modeling effort, and then we can get these maps of SWE in space. And so we've flown several flights in this area through both LBL and through collaborations with the state and through collaborations with SnowX. And I'm going to highlight 4 of these today, one during an average year, 2016, during peak snow water equivalent, 2 during a very dry year in 2018, and then 1 just for visual in 2019, which is a very wet year. So ASO makes for just great images, and so I can't resist using Jeff Deems, who's our principal snow hydrologist, use some of his images. So we're going to use some of his beautiful ASO images to kind of highlight snow distribution processes. Before I get going, though, I like to do a little sidetrack. We do on the left-hand side of your screen. This is just a show that we go out into the field, and we've done these fairly large-scale campaigns in space and also in time, collecting snow pit data to not only validate ASO, but to also collect chemistry and snow and water isotopes. The water isotopes are depth resolved. I'm currently working on this data set over 5 years to drive isotopic fractionation modeling and trying to understand how water isotopes are entering into the watershed, and we'll be using this to help us in terms of hydrologic partitioning to plant transpiration, recharge into streams as well. But back to ASO on the right-hand side of your screen, this is sort of like the 30,000-foot view of snow distribution. Deep snowpack is shown in red, and the shallow snowpack is shown in blue. And what you immediately see is there are these strong elevational gradients in the system. High elevations have deep snowpack, low elevations have low snowpack. And these lapse rates are often how we like to parameterize our hydrologic models. We put in a precipitation lapse rate with deeper snow, more precipitation happening at elevation. But if we zoom in on, say, this part of the image, this is called Democrat Basin, we start to see that assuming a simple elevational lapse rate is perhaps not the best way to go. And this is because snow can be moved across the landscape. It doesn't necessarily stick to where it fell. Wind is a dominant factor here. It moves snow off the ridges. We see this in the blue right here. And the prevailing wind is west to east. And then it dumps the snow down the wind gradient on the northeast aspects of these mountains. And we see these deep snowpacks then building up in these cirque regions of these mountains. The other way that we move material around in terms of snow is through avalanches. And we have a fairly significant avalanche terrain as shown here, where avalanches have scoured these steep hill slopes and moved snow down into the receiving valley. So again, precipitation in terms of snow doesn't stick with where it falls. It gets moved around, and that movement becomes somewhat important. In addition, just as a side note, this just came out 2 days ago. The Colorado Sun just had an article stating they're using these types of techniques like ASO to try to better understand avalanche hazards, which if you're a backcountry fan, this is great, and it will help us better enable safe backcountry travel. And lastly, just for fun, I want to just highlight that you can actually have redistribution by humans too, in terms of like snowmaking. Now, this is not an important component in my project, but I just wanted to show the power of ASO. Again, this is the East River wrapping around the ski resort, and you can see where they've made man-made snow or moved snow around to make snow parks here, ski parks, and also to highlight this is where the Butte Snowtel Station resides. So kind of to get into the science now, the East River, where I'm doing much of my modeling work, is delineated here on the left-hand side. It's about 84 square kilometers to give you a sense of scale. And back in the late part of the season of 2014, the beginning of the 2015 water year, I began to instrument all of the major tributaries to the East River, including the downmost stream gauge, which we call the pump house, or listed as PH here. And began to collect and build rating curves and to collect stream chemistry as well as the stable water isotopes from daily to weekly timescales. In addition to our infrastructure also includes the Snowtel network that I've just been talking about. We have 4 Rocky Mountain Biological Laboratory weather stations that reside within the domain. I can get at wet deposition chemistry from an EPA CastNet station. I set up 4 rain gauges throughout the basin to capture geospatial controls on rain chemistry, but primarily the water isotopes. I did snowmelt lysimeters at 4 locations to get at snowmelt isotopic chemistry. And then we have access to deep wells, shallow wells. And then part of my talk today is going to be talking about ages. And so I got funding through the USGS to collect age dating across a variety of groundwater subcomponents. But I'm mostly going to focus on this dot here in Copper Creek, where we ran a base flow experiment in terms of age dating. So the first paper we really kind of put together was how do we use all this wonderful data to get at some sort of stream water source? Where is the stream water coming from? And so Lindsay Bierup and I took all this data for 2016, which is an average water year, and we set up end-member mixing analysis, or EMMA. So what EMMA does is it takes, we takes a multidimensional problem. In our case, we use 7 different types of water chemistry constituents, and we use PCA analysis to collapse it into 2 dimensions. So to kind of illustrate how this works, the stream chemistry down at Pump House is shown here on the bottom right corner of your slide. And it's moving through this 2-dimensional space as a function of its hydrographic characteristics. So B stands for base flow in the hydrograph, R and F are the rising and falling limb during snowmelt, and M stands for monsoon. And you can see this stream chemistry moving through this 2-dimensional space as a function of those hydrographic characteristics. So base flow is closer to groundwater, rising and falling limb are closer to the snow, and then the monsoon events are closer to the rain chemistry. What I'm interested in, wrong direction. What I'm interested in is the fraction of that stream water that's coming from groundwater. And we use hydrograph separation within this two-dimensional space to derive that. And we do this for all the different gauges illustrated on the left-hand side of your screen. So we developed the fraction of annual groundwater coming into each of those, from each of those tributaries, as well as at pump house. And this is all I did. I simply threw these up against the wall and see what sticks with regards to sort of watershed or sub-watershed characteristics. So one of the things that pops out is the fact that the fraction of groundwater across the watershed is directly related to the volume of snow water equivalent. So this is scale dependent. It's also nonlinear. But what it's basically saying is larger sub-watersheds, watersheds are going to have more groundwater than smaller. We also saw indirect relationships to cover type, specifically the percentage of that subbasin that's covered by conifer, such that those that are covered by a lot of conifer have low fractions of groundwater. And also we saw an indirect relationship with the canopy density, so that those forests that have dense conifer or dense canopy density, they have very low groundwater. I've also highlighted Copper Creek, which we'll keep coming back to. This has an average annual groundwater estimate from Emma of about 1/3 of its annual water budget. So what is Emma telling us? It's an inference because this is very empirical. But what the concentration discharge analysis is kind of hinting at is that recharge or groundwater flow to streams is probably maybe happening in this transition zone called the upper subalpine. The upper subalpine I'm delineating here in the graph with the red box, as well as in this big image on this photo on the far left. This is an area where we have a mixture of barren and low density conifer forests. It's also where most of the snow accumulates and it persists. And we hypothesize that then it melts quickly, it exceeds yield, it generates recharge. And this is why those basins with a lot of subalpine tend to promote more groundwater flux to streams. But of course, this is an empirical idea. And I said, well, now let's move to a more mechanistic approach. Let's build a hydrologic model. Let's have that model run over multiple decades. And I'm going to use GS-Flow. GS-Flow is a model that has its land surfacey kind of model. Is called PRMS. This is a USGS code. And PRMS is going to be what we use to do all the sort of surface, sort of a semi-empirical distributed model. And we're going to use this to model snowpack. And it allows us to account for water and energy budget of forests and sort of the soil zone and whatnot. We use a snowtail network to move our climate through time. And then I use the ASO flight to help me distribute that precipitation of the snowfall. Because remember, snow doesn't necessarily end up where it fell. It gets redistributed by wind and avalanche and other processes. And so if we compare snow simulated, this is observed, in the middle. This is the ASO for a very dry year at peak snow water equivalent and also a much later meltout date. And we compare it to simulated PRMS for the same dates. We see that while the model is not perfect, it's certainly capturing some of these where snow accumulates and also persists even in a very dry year in these high cirque valleys. And so I was pretty excited about these results and that we're doing a pretty good job on capturing snow water equivalent, even with a relatively simple snow model. So the next step was to add the groundwater model and put these together. So again, GS-Flow, we decided to do this only in Copper Creek as a proof of concept. The model is arbitrarily set, it's 400 meters deep, so very deep. And it has 12 layers, with the layers getting deeper as you go further into the subsurface. And it represents 9 hydrostratigraphic units. So the geology here, we'll come back to this over during the age dating, but the upper portions of the model are predominantly a tertiary granodiorite or the white rock pluton. This is upturned, these sedimentary layers of higher permeability. This is the Gothic and Maroon formation, and push those up in the lower basin. These are more permeable sediments down here. So with this coupled model, I can now look at seasonal surface and seasonal surface water and groundwater interactions. So this is an image I always use. This is from Justin Huntington and Rich Neiswanger's 2012 paper. It just highlights the things that I can model nicely. So specifically, we're going to talk about interflow quite a bit. Interflow is that shallow, sort of ephemeral flow that is generated largely through permeability contrast. It's in the soil zone and the saprolite zone, but it's also can be caused by a water table elevation that rises up into that zone. I can model a recharge down to the saturated groundwater. I can model changes in groundwater storage as well as fluxes to and from the stream with the groundwater system as a function of differential gradients. And in addition to soil ET, sublimation, and canopy evaporation, with GeoFlow, I can also capture phreatophytic groundwater ET. So the model is calibrated, and I just wanted to show you that it's calibrated to solar radiation and of course to the snow processes, but also to stream flow, with the black dots indicating actually observed stream flow in Copper Creek, and the gray dots here representing a simple regression with a downstream USGS gauging station. And to show that we're doing a fairly good job mimicking the stream flow and capturing also long-term interannual variability in that stream flow. So now we can take the model, if we feel good with it, and start asking questions about it. And so this slide is relatively busy, but it's a nice slide in the sense that it allows us to compare water budgets across aridity gradients. So aridity here is defined as potential ET or PET divided by P. So a low aridity is going to be a wet and cool year, and high aridity is going to be a warm and dry year. And so we're going to look at these water budget terms. These are aggregated across the whole watershed for a given water year. And what you see on the left-hand side is the ratio of ET, evapotranspiration, to precipitation. It increases as a function of aridity, but at a decreasing rate. So it's very much of a Baduco formulation. It falls slightly below the Baduco formulation because it's very seasonal and very steep watershed. In addition, it's just very responsive. And if we look at stream flow, broken up into surface runoff and interflow, that shallow flow, we see it too is very responsive to the aridity gradient. It declines at a decreasing rate. And its relationship is tightly coupled to ET, with ET primarily in the soil zone, which is where interflow occurs. In contrast, groundwater doesn't show huge variation with aridity. It's fairly stable. But what is really interesting is that on average, over a multi-decade simulation, the fraction of groundwater in the system on average is 35%. If you compare that with the independent work on the EMMA analysis at 33%, it's kind of a nice check that maybe we're in the ballpark. But the groundwater, the fraction of groundwater, I should say, is highly dependent on interflow. If there's a lot of interflow, then the fraction of groundwater is low, maybe representing 21% of the annual water budget. If it's a very wet or hot and dry year, groundwater might represent up to about 50% of stream flow that year. So now the second question I wanted to talk about was what is controlling recharge in the basin on a spatial variability of recharge in the basin. And so what I'm showing you here is a simulated recharge on the far left-hand side of your screen, with red being very low recharge. This is annual recharge, total annual recharge, and blue being high recharge up here in these upper elevations of the basin. It's often you'll see that you want to link recharge to say some, accumulation, snow accumulation metric, or maybe snowmelt, like average snowmelt or maximum snowmelt rate. And so here's a plot of snowmelt, also with blue being high snowmelt and red being low snowmelt. If you look at the regression between GeoFlow generated recharge and its estimate of estimated recharge just using predicted melt, we see that we don't get a great relationship. Snowmelt is only, to predict recharge, only has an R-squared value of 0.33. You can kind of squint maybe and look and see, well, maybe recharge is well defined by snowmelt when recharge is low, but it's not doing a good job predicting recharge when recharge is very high. So I started looking around at the different water budget terms in the GeoFlow model, and I eventually fell upon interflow. Interflow, again, shallow water moving through the system, ephemeral. If we include inflowing interflow moving from cell to cell, we can improve our predictive ability to an R-squared value of 0.78. If we look at a dry water year, again, this is 2012, red being low recharge, blue being high recharge, we see that these areas of high recharge seem to be somewhat stable, even during the worst water year in our historic record. We see that melt is very low, and we see that the predictive ability of melt to predict recharge is quite poor. And that interflow instead now pulls it all together, having a much greater portion of that predictive capability with an R-squared value of 0.87. So I like to think in pictures. And so I sat down and I drew a sketch and I said, okay, let's look at where recharge is occurring as a function of its landscape position. So just a simple sort of cross-section using from alpine conditions to the subalpine, montane, and riparian zones. This also represents a gradient in aridity as you move from high elevation to low elevation. We know from the ASO and just by being in the field that there's a lot of redistribution. That redistribution tends to move a lot of the snow, the deepest snowpack, the most snow down in this transition zone between the alpine and subalpine, or the upper subalpine. This is that low density conifer forest. This then in turn drives snow recharge, but it cannot explain all that high elevation recharge. Instead, we also need to redistribute snow melt through the soil sort of saprolite zone, this weathered zone. We need to move this down and also supplement recharge with that melt to drive the highest recharge in the basin that is somewhat decoupled from interannual variability and able to buffer the highest recharge zones during those periods of very large drought. Lower in the basin, we can generate recharge as well. It's much lower. It's very much tied to interannual snowpack variability. It tends to occur prior to peak consumptive demand of the vegetation, but and then we support that later season vegetation ET through interflow. All right, so the last thing I wanted to talk about is how old is base flow? Base flow being that late season summer flow and winter flow that's predominantly groundwater. Age is important. We care about age because it is a nice sort of metric to try to understand lag in the system and vulnerability of that system to change. And it's also really important in terms of biogeochemistry. And I'm going to use it explicitly to help try to understand subsurface properties, since I don't have any real data or I don't have any wells in this system. This is mostly in the wilderness. So I'm going to rely on the integrated hydrologic model that I just presented to help describe my hydrologic stores and fluxes. I'm going to use particle tracking to get at groundwater age distributions, and they're going to be weighted by those groundwater fluxes. And then I'm going to discuss now this dissolved gas tracer experiment that was originally developed by Ward Sanford with the USGS, but never applied to a system like Copper Creek, which is much more steep and much more turbulent. So the way that Sanford had set up his experiment to actually age date the stream flow directly is you go out into the field, and Dave Marchetti from Western Colorado University was a great help on this, because collecting these samples, there's a lot of water samples. SF6 samples, for instance, are about 1 liter each. So it's a lot of water, haul in and out of the wilderness zone. But we went out and collected gas tracers, 4 of them: nitrogen gas, argon, SF6, and CFCs, specifically CFC 113. And we collect these hourly for 12 hours. And we use Ward Sanford's approach. I hate equations in presentations, but we use this approach to then constrain the residence times of each of these gases within the water column itself. So we need 4 of the gases to do this. And we also know, at least regionally, what our atmospheric concentrations are. And through this experimental approach, we can assign, calibrate a unique age distribution with the data, backing through a convolution, using a convolution integral to get at using the atmospheric inputs. So that was the grand plan when I started out. In addition, I also collected perennial data from perennial springs, specifically SF6 and dissolved gases, and came in with an average age of those springs at about 10 years. Well, just to let you know, science doesn't always go the way you want. And what ended up happening is the nitrogen argon gas really were approaching atmospheric equilibrium. In other words, they were providing no additional information. So I really had only half the information. I hand waved my way through that, submitted a paper, was rejected, and I was like, oh, what do I do? So Andy Manning with USGS said, you know, maybe Ro, you can you can salvage this and think about this in reverse. What do you have and what do you not have? Well, what I have is I have a model that predicts the age distribution using particles that is defined by the hydrology and geology defined in the model. I can take that age distribution, I can run it through the convolution integral and see if I get the observed stream concentration. If I can do that with significance, then my model is pretty good. If I cannot, then I'm going to need to recalibrate the model and reassess that conceptual model. So essentially, we're flipping the model in reverse from the initial conceptualization. So just to kind of walk through this relatively quickly, GISFlow original model is shown over here. These are the particles I drop in the system. I drop them on top of the model. I let them run through, and they're color coded by how old they are when they hit the stream. So blue is very, very fast, very young water, and then the warmer colors are much older. And then this is our sampling location, CCO3. And so it primarily represents this sort of upper area, this upper granodiorite, lots of snow, very low permeability bedrock. And what ends up happening is we have this hyperlocalized, very young groundwater moving through the system. That's our initial conceptual model. The age of that base flow, which also accounts for interflow, on the day of the experiment in late August of 2017 is only 1.5 years. So not, unrealistic in my conceptual mind, but significantly lower than what we had measured in the perennial springs. 63% of the groundwater in Copper Creek is estimated throughout the basin to move through the shallow alluvium, or less than 8 meters deep. And this is kind of the kicker, we cannot predict streamflow SF6 concentration using this conceptual model. So I had to go back and think about this through a relatively robust sensitivity analysis. And the most sensitive parameter is that granodiorite permeability. So with a very slight increase in that permeability, I can increase my median age distribution now goes from 1.5 to 7.5 years. I significantly increase the depth, median depth of groundwater flow from less than 8 to 10 meters to 100 meters. But now I'm able to meet this SF6 water column concentrations in streamflow with statistical significance. So it fundamentally shifted the conceptual hydrologic model that I had put forth earlier. So what does this mean? What is the interannual variability historically in baseflow age? Again, baseflow contains both interflow from either that winter or maybe from the monsoon, as well as deep groundwater. And if we look at interannual variability in age, it can range from 3 to 12 years. But that age range is tightly controlled by the amount of interflow, right? So if you have a big year like 1995, I would go out and sample in late August, it'd only be 3 years old. But if I went out in 2018, which was a drought year, I would have something closer to 12 years, had very low snow, very bad monsoon year. If I pull the groundwater out of the base flow and just look at saturated flow, I see that groundwater now is fairly stable across the historic record, coming in around 12 years. And it's very stable because it's representing sort of long-term climate and land use in that basin. So if we want to fundamentally shift the age, we're going to fundamentally have to shift the system. And I'm going to shift it in terms of climate. I'm just going to run steady state. So these are steady state results. I'm saying, okay, let's take 1998, let's just alter precipitation. That's all we're going to do. We're going to scale precipitation up, we're going to scale precipitation down. And look at the median age of groundwater. And what you end up finding is that at very wet conditions from the historic median condition, there's not much sensitivity of groundwater age to the amount of precipitation. But when you go drier than the historic median condition, age starts to increase exponentially. I can now warm this climate, and I start to see it too. If we see even under wet conditions, under a warm scenario, very little change in the groundwater age distribution. But as we go to drier conditions, we see that it becomes more sensitive to drying with warming. And because it's a model, we can do whatever we want. We can now force all the snow to rain, which is not realistic, but let's see what happens. And we see that it too remains relatively stable under very wet conditions, becomes exceedingly sensitive under drying conditions from the historic median. So what does this story, what is it trying to tell us? What is the significance of this story? Well, the conceptual model is not mine. This is a conceptual model that I'm presenting that comes from Gleason and Manning and many others, and very nicely presented by Katie Markovich's paper, came out in WRR in 2019. So this is not my conceptual model, but we see that Copper Creek seems to follow along this gradient between topographically controlled groundwater flow systems and recharge controlled groundwater systems. Topographically controlled groundwater systems, these have high recharge and low hydraulic conductivity. Under these scenarios, we have very shallow groundwater, water table depths. We generate these very local flow paths that are young in age, and we produce these perennial streams. And then while the down gradient stream does have influence of some of these longer flow paths, it's still dominated by younger flow. Under recharge controlled conditions, we have either low recharge or high K values, or we have some combination of the two of them. But under these conditions, we see water table elevations drop, ephemeral streams now form, and we now lose those local flow paths. And we're now more reliant on these deeper groundwater flow paths in our stream flow. Now, what the gas tracers showed us is that while Copper Creek, we had originally conceptualized as being firmly and topographically controlled, highly dependent on super fast young water, was incorrect. It's actually probably a little closer to this threshold, and that Copper Creek maybe, at least this is first estimate, is maybe a little bit more vulnerable to climate change in terms of groundwater flow than we had originally conceptualized. So the take-home messages here are we use lots of independent approaches. The independent approaches really suggest similar conceptual models in terms of not only the amount of groundwater reaching Copper Creek, but also on where recharge is perhaps happening, or at least where the dominant mechanism of recharge is happening, which is up in the upper subalpine. We showed that snow accumulation drives the relative amount of groundwater in a stream, and this is primarily through interflow, right? And interflow is strongly coupled to consumptive ET. So in order to understand the relative effect of groundwater in streams, you actually need to understand all the other processes leading to that, including evapotranspiration, soil processes, etc. We found that the feedbacks between seasonal melt and vegetation dynamics are really, really important in the lower elevations of our particular domain, but it is that the topography focuses groundwater delivery, or that shallow interflow down from the alpine into the upper subalpine, and this zone forms that preferential recharge zone that is somewhat decoupled from interannual variability. And then we also see that gas tracer data really helped change our conceptual model of this basin. It seemed to hint that there is a significant portion of hydrologically active groundwater flow at significant depths. It's not all at shallow depths. And it's through these tight units, and it's relatively old. It's on the order of a decade, 12 years or so. And that lastly, that this basin is not buffered necessarily from climate, in the sense that it seems to be all on this precipitation threshold, and it exists currently maybe closer to that threshold than we thought in terms of fundamentally changing those groundwater flow paths. So the last thing I wanted to say, and I'm not going to talk about this, but we have a recent paper out about monsoon rain. So I don't forget about monsoons, but I just wanted to highlight that we have this paper out just recently in GRL, and if anybody wants to ask questions on it, I'd be happy to take it. I just don't have time today to talk about this work. And with that, I'd love to take questions if there's time and interest. So, and then please reach out to me if you don't want to ask questions on Zoom. You can always reach me by email, and I'd love to have a discussion. And that's it.
Thank you very much, Rosemary. That was great. Everyone's clapping, I know it.
Yeah. Everyone's clapping. Yeah.
I know. I don't know if I should stop sharing or not, but there you go.
Great. So we'd love to take questions from the audience. People can either just blurt them out if you're become numb to Zoom like the rest of us and you just pretend that you're only talking to your family, or also feel free to throw stuff in the chat box, and I can help digest that. So please, I'll open it up to questions.
Hey, Ro, this is Katie.
Hi, Katie. Hi, Alex.
Great presentation. I wanted to.
Oh, I can't hear you. I think you muted by accident.
Oh, my bad. I wanted to ask about the climate change simulations. Did you just do sort of like a constant increase, or did you vary the distribution and look at intensity?
What I did there, because it was easier in part, but also because the results had stressed that the groundwater, the transient particle tracking, which is much harder to do and much more time consuming. And I had picked N members in the historic to do that. I didn't do it for every year, so there's some shortcuts there. Had stressed that the groundwater seemed to be relatively stable within the historical context. So I just wanted to jump away from that and said, if we were in a new normal, right? Like, so it's steady state. So I run GS flow, which is the hydrologic model, to quasi steady state until there's very little change in the water balance. And then I use those recharge to drive, and groundwater fluxes to and from the groundwater system to drive the particle tracking. So that's how that was done. So I didn't actually do the transition between one state to the next state. That would be hard. And I haven't done that.
Yeah.
I get stuck in the unsaturated zone. Gets really tricky. It takes forever to stabilize as you go drier. It does a good job going wetter, but it takes forever to stabilize going drier.
Yeah, totally. Makes sense. Yeah, I just wonder, it's such a cool tool you've developed that with this discussion of the West getting drier, there is this question of, what if it's drier, but with more intense rain? What do you see? Are we still on that threshold? But thank you for your answer.
Well, and not just to kind of not shown today, I did look at lots of things in the paper that we put in WRR, which is not just shifting precipitation amount and not changing the timing, but I also looked at different water years and just said, okay, what is there's temporal variability and spatial variability with each water year, right? And also I looked at what if we just assumed uniform, the same mean climate, but it's uniformly distributed across the whole watershed. What happens then? Yeah. And this was sort of looking at some of those changes.
Cool. Thank you.
Yeah.
So Ro, there's some good questions showing up in the chat, and I'll just try to interpret because I know it takes a while to read these things on your own. But the first one was from Jeremy, and he's asking about your thoughts on uncertainty, especially in the GS flow model, and how that influenced your various inferences that you made, such as the particle tracking results.
Yeah, I didn't do a full-blown uncertainty analysis. As you see, I just talked about a sensitivity analysis, in large part because that's also really difficult and time-consuming. And so I kind of hand-waved my way around this by saying, groundwater modeling is non-unique by its inception. It's just highly non-unique. I think I'm trying to get around this by the age dating data because we don't have any on-site subsurface data. And so the age dating starts to put us there. The major limitation, it's not necessarily an uncertainty question, but is the fact of how simply I parameterize the hydraulic conductivity field. So it declines with depth, right? But for a given unit of a given type at a certain depth, it has the same value everywhere. And I think what it's doing is it might be emphasizing those deep flow paths and the really heavy tails in the distribution. And I think that's probably overly simplistic. I'd love to drill a well, like right at the top of the mountain, all the way down to water level. But that's very hard and expensive and impossible to do in some cases. But I do recognize that, and that's one reason we stick with the median age versus the mean age, because then I'm not relying so much on that tail. But yeah, uncertainty and also model structure, these are all issues that are a problem. But this is a conceptual model that I think is worth studying and going out and looking at new tools to try to understand.
Wonderful. Another one, and maybe she'd like to expand on this because I think I get the idea, but Hannah was asking if you used any metrics for the riparian zone in any way, like considering the condition of the trees or ponds and beavers and things along those lines that might have influenced your flow paths.
Yeah, in Copper Creek, I kind of get away from that because it's such a steep, sort of narrow basin. It does have that riparian zone, and that riparian zone is where most of the groundwater ET is happening, right? And so that is part of the solution. So in part, I don't cover it because it's just not that exciting, but it's hard to do, is I have to sort of iterate on that groundwater travel. What is the groundwater age that it's pulling, right? Like, so it's not pretty, but I do that. And that's actually, that area is also the area that struggles to equilibrate in the quasi-steady state. But I think your point, as I'm moving to a much larger domain now, I'm going to about a 750 square kilometer domain that goes down into a much more developed riparian zone as well as agricultural zone. For comparison, Copper Creek is 24 square kilometers, so much bigger domain. I'm hoping that some of those questions could be better answered.
Great. I think we have time for one more, and this is a big and challenging one. Elizabeth was asking, you know, the 35% that you recognized in your system, do you think that's somewhat representative of high alpine systems, or do you think there's a lot of variability if you move to another watershed?
Well, if you look at some of Matt Miller's work, what he did in the Upper Colorado River, our numbers fit within his numbers. So I don't think it's an unreasonable amount. At the same time, I mean, these headwater systems tend to be high recharge, low K, and so there's probably some uniformity there. But I think that this is the challenge of hydrology, right? Moving it out of a specific model for a specific location and generalizing across a much larger swath. And so I think that's a really great question.
Fantastic. We maybe sneak one more in. Will had a pretty interesting one on here. So Will was asking, I think this is a nice one to close it on because it's tying it back to implications. So he's asking, you know, what connections you might be able to make between your results and your management decisions or policies around things like grazing, timber harvest, ag, restoration, et cetera. Do you think at this point you can elaborate on those types of implications?
Well, you know, I can say one of the things I do in my quote free time is I actually serve on the Upper Gunnison River Water Conservancy District. One of the ideas I had there when I first applied for that was that I was going to bring science solutions to water management, right? Like, you know, a very unidirectional kind of idea, just because. And I quickly learned that that is not the way it should be. Like, I need to listen and learn about what are the challenges of water management. And here, a lot of the irrigators in our area are they understand the system. They have generations that understand the system. So there's actually a feedback in the questions and the policy and the management of these systems. So just to emphasize that, get involved in your own local water resources and listen to what your stakeholders are saying. For the students out there, it's eye-opening how little I actually know sometimes. So, or most of the time. The other thing I wanted to emphasize, in our basin, it's predominantly owned by the Forest Service, right? And evapotranspiration, other than streamflow, and this is a wet system, this is not a dry system. Evapotranspiration is a big player from the forest. And so we're really, in terms of management, starting to look at forest health, whether that's fire, beetle impacts, other types of logging management opportunities, and what does that mean? The other thing, so just getting in water balances and overall. The other thing that's really, and I don't want to take too much time, I know everybody has to go, but is we're using the ASO, and we've hired, this is our district, and NCAR is Dave Gotchis. I don't know if people know him, but he's very much involved in the SFA. And he is running a lot of our forecast modeling and comparing it to the Bureau of Reclamation sort of forecasting. Because bad forecasting or inadequate forecasting that's moving because we're falling outside the norm now is causing a lot of hardship on the irrigators and stakeholders. So getting better forecast models is hugely important, informed with ASO and other types of information like that.
Wonderful. So I'll conclude at least this portion, and John might have something else to add, but I'll conclude this portion by saying we don't need to stop here. We've set up another Zoom for some discussion. I'm going to put that link in the chat box here as I speak. So we'll close down the seminar part of the seminar, but for anybody, especially students who are available, please move over to the Zoom that I just provided. We'll probably give Ro 10 minutes to recharge and and use the restroom and whatnot.
I'm just looking now at all the people from all over. Thank you for attending and taking time out of your day. That's fantastic.
Yeah.
Thank you.
Thanks so much, everybody. So yeah, please join us in the next Zoom if you're interested in just some additional follow-up questions. If not, thank you so much for joining us today. A fantastic presentation by Ro on some really wonderful work that she's doing.